Look up at the night sky. Find the brightest stars. Among them, hidden in the southern constellation Centaurus, lies our nearest stellar neighbor, Alpha Centauri, a triple star system just 4.37 light-years away. In cosmic terms, it's practically on our doorstep. And yet, that doorstep might as well be on the other side of the universe. Because here's the thing about space. It's not just big. It's incomprehensibly, soul-crushingly vast. And Alpha Centauri, our closest neighbor, represents perhaps the greatest existential challenge humanity has ever faced. The question isn't whether we can reach it. The question is whether the laws of physics will ever allow us to reach it. Let me put this in perspective. 4.37 light-years. That's the distance light travels in 4 years and 4 months. Light, moving at 186,000 miles per second. The fastest thing in the universe. Nothing can move faster. It's not a suggestion. It's a law. And even at that speed, light takes over 4 years to reach Alpha Centauri. Now consider this. The fastest human-made object ever created is the Parker Solar Probe. It reached speeds of 430,000 miles per hour as it dove toward the sun. Sounds impressive, right? At that speed, it would still take over 6,000 years to reach Alpha Centauri. 6,000 years. That's longer than recorded human history. The ancient Egyptians built the pyramids less than 5,000 years ago. But wait. It gets worse. Much worse. The Parker Solar Probe achieved that speed by using the sun's gravity. It's falling toward the sun, essentially. To reach Alpha Centauri, we need to accelerate away from the sun. We need fuel. Lots of fuel. And here's where the tyranny of the rocket equation comes in. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that mass. It's a vicious cycle. A mathematical prison. NASA scientists have calculated that using conventional chemical rockets, the kind that took us to the moon, you need a rocket the size of the entire solar system to carry enough fuel to reach even a fraction of light speed. And we're not talking about reaching light speed. We're talking about maybe 1% of light speed. At which point, Alpha Centauri is still a 400-year journey. 400 years. Think about that. In 1624, 400 years ago, Manhattan was a Dutch trading post. The Pilgrims had landed just 4 years earlier. If a generation ship had left Earth back then, traveling at 1% of light speed, it would be arriving at Alpha Centauri right now. This very moment. But here's the thing. We don't have generation ships. We can't even build them yet. The technology doesn't exist. The materials don't exist. The life support systems that could sustain human beings for centuries in the void don't exist. We can barely keep the International Space Station running, and that's just 250 miles above Earth. We can call home. We can come back. We have Earth right there, a vast blue safety net below us. Alpha Centauri offers no such comfort. No home. No safety net. Just the infinite darkness between the stars. Now you might be thinking, what about antimatter? Science fiction loves antimatter. And for good reason. When matter and antimatter collide, they annihilate each other, converting 100% of their mass into energy. It's the most efficient energy source theoretically possible. Einstein's famous equation, E = mc², in its purest form. Here's the problem. Antimatter doesn't exist naturally in any meaningful quantity in our universe. We have to make it. And making antimatter is staggeringly expensive. CERN, the European Organization for Nuclear Research, can produce about 1/1000th of a gram per year. 1/1000th of a gram. At current production rates and costs, producing just 1 gram of antimatter would cost about $62.5 trillion. That's trillion with a T. And how much antimatter would we need to reach Alpha Centauri? Conservative estimates suggest we need several tons. Not grams. Tons. The costs would be in the quadrillions. Numbers so large they become meaningless. We're talking about more money than exists on Earth. More energy than human civilization currently produces in decades. But let's say we solve that problem. Let's say we find a way to produce antimatter cheaply and efficiently. We build our antimatter rocket. We accelerate toward Alpha Centauri at a significant fraction of light speed. Let's say 20%. That would get us there in about 22 years. A single human lifetime. Achievable, right? Wrong. Because now we encounter another problem. Space is not empty. Oh, we call it empty. We call it vacuum. But space, even interstellar space, contains matter. Hydrogen atoms, mostly. About 1 atom per cubic centimeter. That doesn't sound like much. But when you're traveling at 20% of light speed, when you're covering 37 million miles per hour, those hydrogen atoms become bullets. They become weapons. At those speeds, a single hydrogen atom carries tremendous kinetic energy. It hits your spacecraft with the force of a bomb. Now multiply that by billions of atoms per second. Your spacecraft isn't just moving through space. It's being sandblasted by atomic particles moving at relativistic speeds. The radiation alone would be lethal. Any biological material would be destroyed. Electronics would fail. The hull itself would erode, atom by atom. To protect against this, you'd need shielding. Massive shielding. Meters thick. Made of materials that can withstand constant atomic bombardment. Materials we haven't invented yet. And that shielding adds mass? More mass means more fuel. More fuel means a bigger rocket. A bigger rocket means more shielding. We're back to the tyranny of the rocket equation. But perhaps the most sobering problem is this. Even if we could reach 20% of light speed, even if we could shield against interstellar radiation, we still have to slow down. We can't just fly past Alpha Centauri at relativistic speeds. We want to explore it. Study it. Maybe even establish a presence there. That means we need to decelerate. And deceleration requires just as much energy as acceleration. Maybe more, because we can't use the sun's gravity to help us slow down. We need to carry fuel not just for the acceleration phase, but for the deceleration phase too. We'd essentially need to double our fuel requirements. And remember, we're already talking about theoretical antimatter engines that would cost more than the entire global economy. Now let's talk about time. Because even in the best case scenario, even if we solve every technical problem, we're still talking about decades. The shortest realistic travel time to Alpha Centauri, using technologies that might be possible in the next century, is probably around 40 to 50 years. One way. No return trip. 40 years. An infant born when the ship launches would be middle-aged when it arrives. The crew that left Earth would not be the crew that reaches Alpha Centauri. It would be their children. Or their children's children. You're asking human beings to commit their entire lives, and the lives of their descendants, to a journey they might not survive. A journey to a place they've never seen. A place that might not even be habitable. Because here's something we often forget. We don't actually know much about the planets around Alpha Centauri. We know the system has at least 2 confirmed planets. Proxima Centauri b, orbiting the smallest star in the system, is in what we call the habitable zone. The region where liquid water could theoretically exist. But that doesn't mean it's habitable. Proxima Centauri is a red dwarf. A small, cool star. It's also incredibly active. It produces massive stellar flares that would bathe any nearby planet in deadly radiation. Proxima Centauri b is probably tidally locked, meaning one side always faces the star while the other side freezes in eternal darkness. The atmosphere, if it exists, could be constantly stripped away by stellar winds and radiation. We don't know if there's water. We don't know if there's an atmosphere. We don't know if the surface is solid or if it's a barren, irradiated wasteland. We're betting everything, decades of travel, countless resources, human lives, on a world we've never even seen up close. And then there's the communication problem. At Alpha Centauri, 4.37 light-years away, every message home takes 4 years and 4 months to arrive. Ask a question, and you'll wait 8 years and 8 months for a response. That's if everything works perfectly. If the communication equipment survives. If there's anyone still listening on Earth, 8 years for a conversation. Think about that. You can't ask for help. You can't get advice. You're truly, utterly alone. More alone than any human being has ever been. More alone than we can really comprehend. But let's step back. Let's look at this from a different angle. Maybe chemical rockets and antimatter engines are the wrong approach. Maybe we need to think differently. Enter the concept of laser propulsion. The idea is elegant. Instead of carrying fuel, you use enormous lasers on Earth, or in orbit around Earth, to push a spacecraft forward using light pressure. Light has momentum. Not much, but it's there. A powerful enough laser, focused on a large enough sail, could accelerate a spacecraft to relativistic speeds. And because the spacecraft doesn't carry fuel, it can be much lighter, much faster. Breakthrough Starshot, an initiative backed by Stephen Hawking and others, proposed exactly this. Build a fleet of tiny spacecraft, each weighing just a gram or so. Attach them to ultra-thin light sails. Then use an array of ground-based lasers, totaling about 100 gigawatts, to accelerate these craft to 20% of light speed. At that speed, they'd reach Alpha Centauri in about 20 years. They'd fly past, taking pictures and measurements, and beam the data back to Earth. Another 4 years later, we'd receive humanity's first close-up images of another star system. Total mission time, 24 years. Achievable within a human lifetime. It sounds perfect. But the challenges are immense. Building a 100 gigawatt laser array would require technology we don't have. The laser would need to be precisely focused across millions of miles as the spacecraft accelerates. Any slight deviation, and the craft misses the beam and is lost forever. And remember, these craft are tiny. Gram scale. They can't carry much in the way of instruments. They can't slow down. They can't orbit. They just fly past at 20% of light speed, taking pictures as they go. And there's another problem. A problem nobody really likes to talk about. At 20% of light speed, these tiny craft become weapons. Relativistic weapons. If one went off course and hit Earth, the kinetic energy release would be catastrophic. We're talking about explosions measured in kilotons of TNT. And we'd be launching thousands of these things. But let's say we solve all of that. Let's say breakthrough Starshot succeeds. We get images. We get data. It's a monumental achievement. First contact with another star system. But it's not exploration. Not really. It's reconnaissance. A flyby. We're not landing. We're not studying. We're not establishing a presence. We're just taking pictures as we screen past at a significant fraction of light speed. To actually explore Alpha Centauri, to land on planets, to study them up close, we need more than gram-scale probes. We need spacecraft. And spacecraft can't be accelerated by lasers because they're too massive. We're back to the fuel problem. Back to the rocket equation. Back to the fundamental limitations of physics. Now, some people, optimistic people, talk about generation ships. Massive spacecraft, essentially flying cities, that could house thousands of people for the centuries-long journey to Alpha Centauri. The idea is that generation after generation would be born, live, and die aboard the ship. Eventually, their distant descendants would arrive at the destination. It's a beautiful idea. Romantic even. But the practical problems are nightmarish. You need a completely closed ecological system. Everything recycled. Air, water, food, waste. For centuries, we've tried building closed ecological systems on Earth. They've all failed. Biosphere 2, a 3-acre enclosed structure in Arizona, couldn't keep 8 people alive for 2 years without external intervention. Now imagine doing that in space. For thousands of people. For hundreds of years. One system failure, one disease, one social collapse, and everyone dies. There's no rescue. No evacuation. No fallback plan. You're asking people to live their entire lives in a metal can, knowing their children and their children's children will do the same, just for the slim hope that maybe, generations from now, someone will reach a planet that might be habitable. And here's the uncomfortable question: would they even want to? Imagine being born on a generation ship. You've never seen Earth. You've never felt rain. You've never stood under an open sky. All you know is the ship. Corridors. Recycled air. Artificial light. Your parents tell you stories about a mission, a destination, but it's abstract. Meaningless. You didn't choose this. You were born into it. Would those generations maintain the mission? Or would they say, why? Why are we doing this? Why are we suffering for a goal we'll never reach, set by people who died centuries ago? There's a real possibility that a generation ship would never reach its destination, not because of technical failure, but because the people aboard simply decided to turn around. Or to stop. To drift in interstellar space forever. But let's talk about the elephant in the room. The thing that really makes Alpha Centauri impossible. The speed of light. It's not just a speed limit. It's the ultimate cosmic barrier. Einstein showed us that as you approach the speed of light, strange things happen. Time dilates. Mass increases. The energy required to accelerate approaches infinity. At 50% of light speed, time aboard your spacecraft would pass at about 87% of the rate it passes on Earth. At 90% of light speed, time slows to about 44%. At 99%, it's about 14%. This is real. This is measurable. We've tested it with atomic clocks on airplanes and satellites. So here's the paradox. If you could somehow accelerate to 99% of light speed, from your perspective, the journey to Alpha Centauri might take only 7 months. But on Earth, 4.5 years would pass. You'd arrive young, but everyone you knew would have aged 4.5 years. At 99.9% of light speed, the effect is even more extreme. For you, mere weeks might pass. On Earth, years. Return to Earth, and you've been gone a decade. Your friends are older. Your family has moved on. You're a temporal refugee, displaced in time. And that's assuming you can reach those speeds, which you can't, because the energy requirements are absurd. To accelerate a single kilogram of mass to 99% of light speed requires about 9 times 10 to the 16th joules of energy. That's about 21 megatons of TNT equivalent per kilogram. A modest spacecraft weighing 1,000 kilograms would require 21 gigatons of energy. That's roughly 400 times the entire annual energy consumption of the United States. For one spacecraft. One way. No deceleration. No return trip. The speed of light isn't just a barrier. It's a cosmic enforcement mechanism. It's the universe saying, no, you cannot do this. You belong to your planet. You belong to your star system. The stars are not for you. And maybe that's the harshest reality of all. Not that Alpha Centauri is far. Not that the technology is beyond us. But that the universe itself is structured in a way that prevents interstellar travel. The distances are too vast. The energy is too extreme. The time scale's too long. We are, in the most literal sense, prisoners of our own star system. But humans are stubborn. We don't accept limits easily. So we dream up exotic solutions. Wormholes. Warp drives. Hyperspace. These are staples of science fiction, and there's a reason for that. They have to be fictional, because the physics doesn't work. Or rather, the physics works in theory but requires things that probably don't exist. Take wormholes. Einstein's general relativity allows for them. A wormhole is a shortcut through space-time, connecting two distant points. Travel through a wormhole, and you could reach Alpha Centauri in seconds. The problem is that wormholes, if they exist at all, are incredibly unstable. They collapse almost immediately. To keep one open, you need exotic matter with negative energy density. We've never observed such matter. We don't know if it exists. Most physicists think it probably doesn't. And even if it does, even if we could stabilize a wormhole, how do you create one? How do you position one end at Alpha Centauri? You'd have to send something to Alpha Centauri first, by conventional means, to set up the wormhole. Which brings us right back to the original problem. It's circular. Wormholes don't solve interstellar travel. They presuppose you've already solved it. What about warp drives? The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical solution that doesn't violate relativity. The idea is that you don't move through space. Instead, you warp space around you. You compress space in front of your ship and expand it behind you. You surf a wave of space-time. Relative to the space immediately around you, you're not moving. But relative to distant objects, you're moving faster than light. It's brilliant. It's also probably impossible. The energy requirements are staggering. Some estimates suggest you need the mass energy equivalent of Jupiter. Recent refinements have brought that down to perhaps the mass of the Sun. Still absurd. And again, you need exotic matter with negative energy density. The same stuff we probably can't get for wormholes. There's also a causality problem. If you can travel faster than light, you can, under certain conditions, travel backward in time. You create paradoxes. The universe doesn't like paradoxes. Most physicists think that any method of faster-than-light travel will either require impossible conditions or will be prevented by some mechanism we don't yet understand. So where does that leave us? Are we truly stuck? Are the stars forever out of reach? Maybe. Probably. The laws of physics are not suggestions. They're not guidelines. They're constraints on reality itself. And those constraints seem designed, almost maliciously, to keep us confined to our solar system. The distances are too great. The speeds required are too extreme. The energies needed are too vast. Every solution we come up with hits a wall. A physical, mathematical, insurmountable wall. And yet we look up at the night sky and we see those stars. We see Alpha Centauri, a pale yellow dot in the southern sky. 4.37 light-years away. Our closest neighbor. We know it's there. We know there are planets there. We know that one of those planets might, just might, be capable of supporting life. And we cannot look away. This is the curse of intelligence. The curse of curiosity. We can see the destination. We can imagine being there. We can calculate trajectories, design spacecraft, plan missions. But we cannot overcome the fundamental physics of the universe. We're like a child pressing their face against a candy store window, seeing wonders we cannot reach, separated by a barrier we cannot break. Some people find this depressing. The idea that we're trapped, that the stars will forever remain distant pinpricks of light, unreachable and untouchable. But maybe there's another way to look at it. Maybe the impossibility of reaching Alpha Centauri is a reminder of our place in the universe. We're not conquerors. We're not destined to spread across the galaxy. We're a single species on a single planet orbiting a single star. And that star, our sun, is all we have. This solar system is our home. Not just Earth. The whole system. Mars is reachable. The asteroid belt is reachable. The moons of Jupiter and Saturn are reachable. These are challenging destinations, yes, but they're within the realm of possibility. We can get there with technologies we have or can develop in the near future. We don't need to break the laws of physics. We don't need impossible energies or exotic materials. We just need engineering, and time, and will. Maybe the message of Alpha Centauri's impossibility is that we should focus on what we can reach. Build habitats on Mars. Mine the asteroids. Establish colonies on Titan. Create a true spacefaring civilization within our solar system. Not reaching for the stars, but making full use of the star we have. Our star. The Sun. Because here's the thing. If we can't even establish a sustainable presence on Mars, a planet just months away, what business do we have dreaming of Alpha Centauri? If we can't build a closed ecological system that works for years, how can we expect to build one that works for centuries? The challenges of interstellar travel are not just technical. They're foundational. We need to learn to live in space before we can dream of living among the stars. And maybe, just maybe, that's enough. Maybe it has to be. Because the universe has spoken. The laws of physics are clear. Alpha Centauri is impossible. Not difficult. Not challenging. Impossible. At least with any physics we currently understand or are likely to understand in the foreseeable future. But humans are dreamers. We've always been dreamers. 10,000 years ago, we looked at the horizon and wondered what lay beyond. We crossed oceans on rafts. We climbed mountains because they were there. We went to the moon not because it was easy, but because it was hard. And now we look at Alpha Centauri and we dream. Maybe future generations will find a way. Maybe there's some loophole in physics we haven't discovered yet. Some exotic principle that allows for faster-than-light travel without violating causality. Some technology so advanced it seems like magic to us. Arthur C. Clarke said that any sufficiently advanced technology is indistinguishable from magic. Maybe Alpha Centauri requires magic. Or what we would call magic today. But here, now, in the early 21st century, with the physics we know, the technology we have, and the resources we can muster, Alpha Centauri is out of reach. It's a beautiful, tantalizing destination. A triple star system with planets, possibly habitable planets, just 4 light years away. But those 4 light years might as well be 4 million. The gulf is too vast. The barrier's too high. The universe itself stands in our way. And so we're left with a strange duality. We're a species capable of understanding the universe, of measuring distances to stars, of calculating trajectories across light years. We can see where we want to go. But we're also a species bound by the same physical laws as everything else. We can dream of Alpha Centauri, but we cannot reach it. We're cosmically aware, yet cosmically confined. We understand infinity, yet we're trapped in finitude. Perhaps that's the final lesson of Alpha Centauri. Not that we should stop dreaming, but that we should dream responsibly. Dream of Mars. Dream of the outer solar system. Dream of sustainable space habitats and asteroid mining and fusion propulsion. These are audacious dreams. They're worthy dreams. They're achievable dreams. Alpha Centauri, for now at least, must remain a dream of a different kind. A reminder of our limits. A monument to the vast and uncaring universe we find ourselves in. A testament to distances so great and energies so extreme that even our most ambitious technologies fall comically short. The stars are not going anywhere. They'll be there in 1,000 years. In 10,000 years. Maybe by then we'll have figured it out. Maybe we'll have found a way. Or maybe we'll have accepted that this solar system, our solar system, is enough. More than enough. A cosmic oasis in an infinite desert. A place where life arose, where consciousness emerged, where a species learned to ask questions about the universe. And maybe that's the greatest achievement of all. Not reaching the stars, but understanding why we can't. Not conquering the cosmos, but comprehending it. Not traveling to Alpha Centauri, but looking at it, 4.37 light years away, and appreciating the sheer, staggering improbability of everything that had to happen for us to be here, looking up, wondering what's out there. Because that's what we do. We're humans. We look up. We wonder. We calculate. We dream. Even when the dreams are impossible. Especially when the dreams are impossible. Alpha Centauri is impossible. But it's beautiful. And maybe beauty, not conquest, is the point. The universe is under no obligation to make sense to us. It's under no obligation to be conquerable. It simply is. Vast. Ancient. Indifferent. And we, tiny beings on a tiny world orbiting a medium-sized star, we look out into that vastness and we ask, can we go there? And the universe, in its way, answers. No. Not there. Not yet. Maybe not ever. But you can look. You can learn. You can understand. And for a species like ours, maybe that's enough. Maybe it has to be. Because Alpha Centauri, our closest stellar neighbor, the nearest other star system, the destination of all our wildest interstellar dreams, is and probably always will be impossible to reach. The journey to Alpha Centauri is not measured in years or even lifetimes. It's measured in impossibilities. And until we overcome those impossibilities, until we find a way to rewrite the laws of physics themselves, Alpha Centauri will remain what it has always been. A point of light in the darkness. Beautiful. Tantalizingly close. And forever out of reach. That's the harsh reality. That's the truth we must face. The stars, for now, are not ours. They belong to the universe. And the universe, it seems, wants to keep them that way. We can look. We can dream. But we cannot touch. Not Alpha Centauri. Not yet. Perhaps not ever. And in the silence of that realization, in the vast empty gulf between Earth and Alpha Centauri, we find a strange sort of peace. We're home. This is our place. This solar system. This star. This planet. And maybe, just maybe, that's where we're meant to be. Not spread across the galaxy like some science fiction empire, but here. Concentrated. Focused. Making the most of the one star we have. The one planet that gave us life. Alpha Centauri watches from the darkness, 4.37 light-years away. Unreachable. Untouchable. A testament to the limits of ambition and the boundaries of physics. A reminder that the universe is bigger than we are. That some dreams, no matter how beautiful, no matter how compelling, may forever remain just that. Dreams. And we, standing on our little world, looking up at that distant point of light, we understand. We accept. And we continue to dream anyway. Because that's what humans do. We dream of the impossible. Even when we know, deep down, that impossible means exactly what it says. Alpha Centauri. 4.37 light-years away. Our nearest neighbor. And the clearest proof that in this universe, distance isn't just a measurement. It's a prison. And we, for all our intelligence, for all our technology, for all our dreams, we are the prisoners. Looking through the bars at a cosmos we can study but never truly explore. That's the harsh reality. That's the truth. Alpha Centauri is impossible. And it always will be. Unless we're wrong. Unless there's something we don't know. Some principle of physics waiting to be discovered. Some revolution in our understanding of space-time and energy and the fundamental structure of reality itself. It's possible. Unlikely, but possible. Humans have been wrong before. We thought the Earth was the center of the universe. We thought heavier-than-air flight was impossible. We thought we'd never split the atom. And yet here we are. Flying. Splitting atoms. Orbiting space stations around Earth and sending probes beyond the solar system. We've done impossible things before. Maybe we'll do impossible things again. Maybe Alpha Centauri isn't the end of the story. Maybe it's the beginning. The first great challenge. The impossible barrier that somehow, someway, we'll find a way to cross. Or maybe not. Maybe this time, the impossible really is impossible. Maybe Alpha Centauri is the universe's way of teaching us humility. Teaching us that we're not destined to conquer everything. That some frontiers are meant to remain frontiers. Forever. Either way, the journey continues. Not to Alpha Centauri. Not yet. But outward. To Mars. To the asteroids. To the moons of the outer planets. Building. Learning. Growing. Becoming a true spacefaring species within our own solar system. And from there, who knows? Maybe we'll find a way. Maybe our descendants, 1,000 years from now, 10,000 years from now, will look back at us and smile at our pessimism. Maybe they'll travel to Alpha Centauri as easily as we travel to another continent. Or maybe they'll look up at Alpha Centauri, just as we do, and feel the same sense of longing and impossibility. Maybe the barrier will still be there. Unbroken. Unbreakable. We don't know. We can't know. All we can do is look up, calculate, dream, and accept that for now, in this moment, with what we know and what we can do, Alpha Centauri is beyond us. Not just beyond our reach, but beyond the realm of physical possibility. And in that acceptance, strange as it seems, there's a kind of freedom. We're not failing because we're not trying hard enough. We're not falling short because we lack imagination or will. We're simply confronting the fundamental nature of reality. And reality, it turns out, has limits. Hard limits. Limits that apply to everyone and everything. Even us. Even with all our dreams and ambitions and technologies. Alpha Centauri stands as a monument to those limits. A beautiful, luminous monument in the southern sky. 4.37 light-years away. Impossible to reach. And yet, impossibly compelling. We'll keep looking at it. Keep studying it. Keep dreaming about it. Because that's what it means to be human. To stare at impossibility and imagine possibility. To confront limits and dream of transcending them. Even when we can't. Even when we never will. The dream itself is the point. The yearning is the message. We are a species that looks at the stars and asks, what if? And maybe, in the end, that question is more important than any answer. Alpha Centauri waits in the darkness. Patient. Eternal. Impossible. And we, standing on Earth, looking up through the atmosphere at that distant point of light, we understand. We know we can't reach it. Not with any technology we have or can imagine developing in the foreseeable future. The laws of physics stand in our way like an unbreakable wall. But we look anyway. We dream anyway. And in that act of looking, of dreaming, of yearning for the impossible, we define what it means to be human. Not by what we can achieve, but by what we dare to imagine. Not by the destinations we reach, but by the destinations we dream of reaching. Alpha Centauri is impossible. But the dream of Alpha Centauri? That dream is ours. Forever. And no law of physics can take that away. The mathematics of despair don't end with distance and speed. There's another problem lurking in the equations. A problem we rarely discuss because it undermines every romantic notion we have about interstellar exploration. Aging. Not human aging. Spacecraft aging. A journey to Alpha Centauri, even in our most optimistic scenarios, takes decades. And spacecraft are not immortal. They break down. Components fail. Radiation degrades materials. Micrometeorites create tiny punctures that accumulate over time. On Earth, we can repair things. In orbit around Earth, we can send up replacement parts. But in interstellar space, halfway to Alpha Centauri, there is no repair shop. No spare parts. No rescue mission. The Voyager probes, our most distant ambassadors, launched in 1977, are already dying. Their plutonium power sources are decaying. Systems are failing one by one. NASA has to shut down instruments to conserve power. And Voyager has only been traveling for 47 years. It's barely left the solar system. The interstellar mission to Alpha Centauri would need to last far longer. 50 years. 100 years. Maybe more. Every component aboard that spacecraft must function perfectly for the entire journey. One critical failure, one computer crash, one power system malfunction, and the mission is over. The spacecraft becomes a tomb. A silent metal coffin drifting through the void, carrying whatever dreams and hopes we loaded onto it, now dead and cold and utterly unreachable. Engineers talk about redundancy. Backup systems. Triple redundancy. But redundancy adds mass. More mass means more fuel. We're back to that equation again. That merciless mathematical prison. And redundancy only delays failure. It doesn't prevent it. Every system, no matter how well designed, has a mean time between failures. Over decades, over centuries, those failures accumulate. They cascade. Eventually, inevitably, something critical breaks. And when it does, the mission ends. Not with drama. Not with explosions. Just silence. A spacecraft that stops responding. Data that stops flowing. A dream that quietly dies in the darkness between stars. But let's imagine we solve that too. Let's imagine we build spacecraft so reliable, so robust, that they can function for a century without maintenance. We still face another problem. Navigation. At interstellar distances, navigation becomes a nightmare of precision. When we send probes to Mars or Jupiter, we can track them constantly. We can see where they are. We can send course corrections. The distances are manageable. Light travel time to Mars is between 4 and 24 minutes depending on orbital positions. To Jupiter, between 35 and 52 minutes. We can have meaningful communication. We can adjust trajectories. But to Alpha Centauri? 4 years for a signal to reach the spacecraft. 4 more years for a response. 8 years for a conversation. If something goes wrong, if the spacecraft drifts off course, if an unexpected gravitational perturbation nudges it slightly, we won't know for 4 years. And then it takes 4 more years for our correction commands to arrive. By that time, the spacecraft could be millions of miles off target. The entire mission could be lost because of a tiny navigational error we couldn't correct in time. And here's the really terrifying part. Space is not static. Stars move. Alpha Centauri is not sitting still, waiting for us. It's moving relative to the Sun at about 22 kilometers per second. Over the decades of travel time, that motion becomes significant. We can't aim at where Alpha Centauri is now. We have to aim at where it will be decades from now. We're shooting at a moving target from an impossible distance with a bullet that takes decades to arrive. The precision required is beyond anything we've ever attempted. Miss by even a tiny fraction of a degree at launch, and billions of miles later, you're nowhere near your target. You fly past the Alpha Centauri system completely, unable to stop, unable to turn around, doomed to drift into the infinite dark beyond. $1 trillion mission. Decades of work. Human lives, if we're talking about a crewed mission. All wasted because of a navigational error smaller than the width of a human hair as measured from Earth. And then there's the radiation. We keep coming back to radiation because it's an ever-present threat in space. On Earth, we're protected. The magnetosphere deflects most cosmic rays. The atmosphere absorbs what gets through. We're safe. In low Earth orbit, astronauts on the International Space Station still have some protection. They're within Earth's magnetic field. They can take shelter during solar storms. But in deep space, there's no protection. Cosmic rays, high-energy particles from supernovas and active galactic nuclei, constantly bombard everything. These aren't like the radiation from nuclear power plants. These are particles moving at near light speed, with energies so high they can punch through anything. They can penetrate meters of shielding. They damage DNA. They cause cancer. They degrade electronics. They create false signals in computers, potentially causing critical errors. The longer you're exposed, the worse it gets. Astronauts on the Moon spent a few days in this environment. A journey to Alpha Centauri means decades of exposure. Even with shielding, even with the best protection we can devise, the cumulative radiation dose would be lethal. If humans are aboard, they'll develop cancers. Multiple cancers. Their immune systems will fail. They'll go blind from cataracts. They'll suffer neurological damage. They'll arrive at Alpha Centauri. If they arrive at all, as radiation-damaged shadows of the people who left Earth. Some scientists have proposed using water or hydrogen as shielding. Thick layers of it surrounding the habitable sections of the spacecraft. Water is effective at stopping radiation. But we're back to the mass problem. Water is heavy. Shielding the entire habitable section would require tons of water. Tons of mass that needs to be accelerated and decelerated. The rocket equation strikes again. Others suggest using magnetic fields to deflect charged particles, mimicking Earth's magnetosphere. But generating a magnetic field strong enough to protect a spacecraft requires enormous amounts of energy. And that energy has to be sustained for decades. Where does it come from? Solar panels are useless beyond the orbit of Jupiter. The Sun is too dim, too distant. Nuclear power? You'd need reactors that can run flawlessly for a century. We've never built anything like that. And even if you could generate the field, even if you could sustain it, it only protects against charged particles. Neutral particles, high-energy photons, they pass right through. There's no perfect solution. Only partial solutions. Trade-offs. Compromises that still leave you vulnerable. But perhaps the most psychologically disturbing aspect of an Alpha Centauri mission is the isolation. The complete and utter separation from everything human. Earth becomes a pale blue dot within days of departure. Within weeks, it's invisible. Just another star in the sky. And then, as you continue outward, even the sun begins to dim. The familiar constellations distort and change as your perspective shifts. You're in a spacecraft, a tiny bubble of life, surrounded by infinite vacuum. Outside the windows, if there are windows, is nothing. Black. Empty. The stars don't twinkle in space. They're just unwavering points of light. There's no sense of motion because there's nothing to move past. You could be traveling at thousands of miles per second and feel like you're standing still, motionless in an endless void. Days become weeks. Weeks become months. Months become years. The routine is suffocating. Wake up. Check systems. Exercise to prevent muscle atrophy. Eat recycled food. Perform your assigned tasks. Sleep. Repeat. For decades. The same people. The same walls. The same recycled air. No new faces. No new places. No escape. Psychological studies of isolated environments, submarines, Antarctic research stations show that humans struggle with prolonged isolation even when they know rescue is possible. Even when they know they can leave eventually. But on a spacecraft to Alpha Centauri, there is no rescue. There is no leaving. You're committed. For life. There's only forward. Only the mission. Only the void. Some crew members would crack. It's inevitable. Depression. Anxiety. Psychosis. Interpersonal conflicts that escalate because there's no escape from each other. On Earth, if you hate your coworker, you go home. You take a vacation. You quit. On a spacecraft, you're trapped with them. For decades. Every annoying habit. Every personality clash. Amplified by proximity and time and the knowledge that this is forever. And what about purpose? What keeps you going? The crew that launched New Earth. They had memories. Families. Friends. A life they left behind. But their children, born aboard the ship, have no such memories. Earth is an abstraction. A story their parents tell. And Alpha Centauri? It's still decades away. An abstraction in the other direction. These children live in the between. Not from Earth. Not yet to Alpha Centauri. Suspended in the void. Do they care about the mission? Do they even understand why they exist? They didn't choose this life. It was chosen for them before they were born. There's a term for this in ethics. Involuntary existence. Creating a person and placing them in a situation they cannot escape and did not consent to. It's morally murky at best. And on a generation ship, it's unavoidable. You're condemning generations of humans to live and die in a spacecraft, for a goal they had no part in choosing, simply because their ancestors decided to go to Alpha Centauri. Some of them will resent it. Some will rebel. What happens then? Do you force them to continue the mission? Do you imprison dissenters? Execute them? The social dynamics become dystopian quickly. A generation ship isn't a utopian dream of exploration. It's more like a prison. A flying prison where the inmates are born behind bars. And let's talk about genetics. A population aboard a spacecraft is necessarily small. A few hundred people at most. That's not enough genetic diversity for long-term health. Over generations, genetic problems accumulate. Recessive genes become expressed. Inbreeding, even if carefully managed, leads to genetic disorders. You'd need a genetic database and artificial reproduction technologies to maintain diversity. But that means controlling who reproduces with whom. Eugenics. Forced breeding programs. Ethical nightmares. Every solution to the Alpha Centauri problem creates new problems. It's fractal. You zoom in on one issue, solve it, and 10 more emerge. The rocket equation. Radiation. Navigation. Aging spacecraft. Psychological isolation. Genetic bottlenecks. Each one insurmountable on its own. Together they form a wall so high, so thick, that it might as well be infinite. And we haven't even talked about what happens when you arrive. Let's say, against all odds, a spacecraft reaches Alpha Centauri. It's traveled for 50 years. 100 years. The crew, if there is a crew, has lived their entire lives in transit. Now they're here. Now what? Proxima Centauri b, the planet in the habitable zone, is tidally locked. One side always faces the star. That side is scorched. The other side is frozen. The only potentially habitable region is the terminator, the narrow band between eternal day and eternal night. And that's assuming there's an atmosphere. Assuming there's water. Assuming the radiation from stellar flares hasn't sterilized the surface. They need to send probes down. Study the planet. Determine if it's actually habitable. And if it's not? If they've traveled 100 years to a dead, irradiated rock? What then? They can't go back. They don't have the fuel. They don't have the resources. They're stuck. Orbiting a planet they can't use, in a star system they can't leave, slowly dying as their systems fail and their supplies run out. Even if the planet is habitable, landing is a nightmare. They need descent vehicles, landing gear, supplies to establish a base. They need to carry all of this with them from Earth, adding to the mass, adding to the fuel requirements. And once on the surface, they're alone. Completely alone. Earth is 4 light years away. A message home takes 4 years to arrive. A response takes 4 more. 8 years for help that probably can't arrive anyway. If something goes wrong, if the habitat fails, if crops don't grow, if water can't be extracted, they die. There's no backup plan. No rescue. No second chance. They're the most isolated humans in history. Further from help than anyone has ever been. Further than anyone should ever be. And what about Earth? What about the people who stayed behind? The mission launches. Years pass. Decades pass. The people who planned the mission die. New generations grow up. Priorities change. Governments change. Funding dries up. Maybe people lose interest. Maybe they forget. The spacecraft becomes a historical footnote. A relic of an optimistic age when we thought we could reach the stars. By the time the spacecraft arrives at Alpha Centauri, the people on Earth who sent it are long dead. The civilization that launched it may have transformed beyond recognition. And when the signal comes back, for years after arrival, announcing success or failure, does anyone still care? Is anyone still listening? There's a real possibility that a mission to Alpha Centauri would be forgotten. Lost not to technical failure, but to simple human indifference. Time erodes interest. Generations grow up with new concerns. The spacecraft becomes invisible. A ghost mission to a forgotten destination. And the people aboard, if there are people aboard, are ghosts too. Transmitting to a home that's moved on. This is the existential horror of interstellar travel. Not just the physical challenges, but the temporal ones. The mission outlasts the civilization that launched it. The goal outlasts the interest. The people involved are separated by time as much as space. They become historical artifacts while still alive. Dinosaurs from another age, still technically functioning but utterly disconnected from the world that created them. And maybe that's why we haven't done it. Maybe deep down, we understand that Alpha Centauri isn't just physically impossible. It's psychologically, socially, economically impossible. It demands sacrifices we're not willing to make. Resources we don't have. Commitment across timescales that exceed human attention spans. It asks us to care about something that won't matter for generations. And we're not good at that. We're good at quarterly earnings. Election cycles. 5-year plans. Not century-long missions. Alpha Centauri requires a patience we don't possess. A dedication we can't sustain. A willingness to sacrifice for a future we'll never see. And that might be the most impossible thing of all. Not the physics. Not the engineering. But the simple human inability to commit to something that long. That distant. That uncertain. We are creatures of the present. We live in the now. Our brains evolved to handle immediate threats and immediate rewards. Hunt the mammoth today. Gather the berries today. Survive today. We're not built to think in centuries. Even planning a decade ahead feels abstract. A century? Multiple centuries? It doesn't feel real. It's too far removed from our lived experience. And so Alpha Centauri remains a fantasy. A beautiful fantasy, but a fantasy nonetheless. We can draw up plans. We can run simulations. We can design theoretical spacecraft and theoretical missions. But bringing it from theory to reality requires crossing a chasm we've never crossed. Not just in technology, but in commitment, in patience, in collective will sustained across lifetimes. Maybe we'll do it someday. Maybe some future civilization, more patient, more committed, more unified than ours, will look at Alpha Centauri and say, yes, we're going. And we'll accept the costs. All of them. The money. The resources. The lives. The time. The uncertainty. We'll launch a mission knowing we won't see it succeed. Knowing our grandchildren won't see it succeed. Knowing our great-great-great-grandchildren will be the ones to finally arrive. And we'll be okay with that. We'll accept it as necessary. As worthy. But that civilization? It's not us. Not yet. Maybe not ever. We're still learning how to work together on our own planet. Still struggling with problems that could be solved if we just cooperated. Climate change. Resource distribution. Conflict. If we can't solve these, if we can't even manage our own world, what business do we have reaching for another? Alpha Centauri doesn't just test our technology. It tests our character, our values, our ability to think beyond ourselves. And so far, we're failing that test. Not because we lack intelligence, but because we lack unity, patience, perspective. The stars demand more from us than we're currently capable of giving, and so they remain out of reach. Points of light in the darkness. Beautiful. Mysterious. Forever beyond us. Alpha Centauri sits there, 4.37 light-years away, not mocking us exactly, but reminding us of what we are. Finite beings. Time-bound. Planet-bound. Limited. Dreaming of infinity but trapped in finitude. Reaching for eternity but constrained by mortality. That's the harsh reality. Not just that Alpha Centauri is far, but that we are small. Too small for such a journey. Too brief. Too divided. Too human. And the universe, vast and ancient and utterly indifferent, simply continues on. The stars shine. Space expands. Time flows. And we, tiny and temporary, look up and wonder what it would be like to go there. Knowing we cannot. Knowing we probably never will. The silence of space carries its own terror. We think of space as empty, but emptiness implies absence. Space is presence. The presence of nothing. And in that nothing, sound cannot exist. No air to vibrate. No medium to carry waves. On Earth, silence is temporary. There's always something. Wind. Distant traffic. Your own heartbeat. But in space, true silence reigns. Absolute. Perfect. Eternal. Now imagine living in that silence for decades. Every mechanical hum amplified by contrast. Every human voice precious because it's the only sound that isn't machine. Every moment of quiet filled with the awareness of the infinite soundless void just beyond the hull. It's not peaceful. It's oppressive. The silence presses in. It becomes a presence. A weight. Astronauts who've spent time in space talk about this. How silence becomes tangible. How you can feel it. And they were only away for months. They knew they were coming home. Now extend that to years. To a lifetime. To generations born into silence and dying in silence. Never hearing rain. Never hearing wind through trees. Never hearing ocean waves. Just the artificial sounds of a spacecraft, and the breathing of the same people, day after day, year after year. Some sounds would drive you mad through repetition. The air recycling system. The hum of computers. The footsteps in the corridor that you hear 1,000 times a day. On Earth, we have variety. New sounds. Unexpected sounds. But on a spacecraft, every sound is catalogued. Known. Expected. There are no surprises. And the human brain craves novelty. Needs it. Without it, we deteriorate. Sensory deprivation experiments show this. Put someone in an environment with no stimulation, and they start hallucinating within hours. The brain manufactures stimulation when none exists. Now imagine decades of limited stimulation. The same views. The same sounds. The same smells of recycled air and human bodies and synthetic materials. Your brain rebels. It creates phantom sensations. You see things that aren't there. Hear voices. Feel touches. The line between reality and hallucination blurs. And there's no cure. No treatment. You can't take a vacation. Can't change your environment. This is your environment forever. Some crew members would retreat into madness as a refuge. A way to escape the monotony. And once you've lost someone to psychosis, what do? There are no psychiatric hospitals in space. No medications except what you brought. No therapist except maybe another crew member with basic training. You're managing serious mental illness with inadequate resources in an environment that caused the illness in the first place. The ethics become impossible. Do you sedate them? Restrain them? What if they become violent? What if they sabotage critical systems? On Earth, we have infrastructure for this. Hospitals. Police. Legal systems. In space, you have nothing. Just desperate people making desperate choices, hoping they don't have to make the choice that haunts them forever. And let's address the mathematics of survival. A closed ecosystem must recycle everything. Water. Air. Waste. Nothing can be lost. On Earth, ecosystems are open. Energy comes from the sun, water comes from rain. We have buffers. Reserves. Margins for error. On a spacecraft, there are no margins. Every molecule matters. Lose too much water to a leak, and you die of thirst. Lose too much oxygen, and you suffocate. The carbon dioxide scrubbers fail, and you're poisoned by your own breath. We've tried building closed ecosystems. Every attempt has revealed the same problem. They drift. Slowly, inexorably, they move away from equilibrium. Oxygen levels drop. Or rise. Carbon dioxide accumulates. Or becomes too scarce. Nitrogen compounds shift. The system, despite all monitoring and adjustment, refuses to stay stable. It's chaotic. Unpredictable. After a year, after 2 years, the imbalances become critical. Biosphere 2 failed at this. The most sophisticated closed ecosystem experiment ever attempted, and it couldn't maintain 8 people for 2 years without outside intervention. Now scale that up to a spacecraft. To hundreds of people. To decades. To no possibility of outside intervention. The complexity becomes impossible to manage. Too many variables. Too many interactions. Too many ways for the system to drift into catastrophic failure. You'd need computers monitoring everything constantly. Adjusting. Compensating. But computers fail. Software has bugs. Sensors give false readings. What happens when the monitoring system itself becomes unreliable? How do you know what's real? The system says oxygen is fine, but maybe the sensor is broken and oxygen is actually dropping. Do you trust the machines? Or do you trust your own feelings? Your own judgment? And if crew members disagree, how do you decide who's right? These aren't hypothetical problems. These are the real challenges of a century-long mission. And every challenge has life or death consequences. There's no room for error. No second chances. One mistake, one malfunction, one misreading, and everyone dies. The pressure is unbearable. Constant. Relentless. You can never relax. Never let your guard down. Because the void is always there, just beyond the hull, waiting for you to make a mistake. And then there's the question nobody wants to ask. What if we're alone? What if Alpha Centauri has no life? No civilization? No answers? We've built this entire fantasy of interstellar travel around the assumption that reaching another star system matters. That we'll find something valuable. Something meaningful. But what if we don't? What if Proxima Centauri b is just a rock? Tidally locked. Irradiated. Dead. What if Alpha Centauri A and B have no habitable planets at all? What if we spend a century traveling to a system that offers nothing we couldn't find in our own solar system? Minerals? We have asteroids. Energy? We have the sun. Living space? We could build habitats in the asteroid belt more easily than traveling to Alpha Centauri. The only thing Alpha Centauri offers that we can't get here is the achievement itself. Proof that we could do it. But is that enough? Is bragging rights worth the cost? Worth the lives? Worth the resources? We could terraform Mars with less effort. We could build rotating space habitats. We could establish a genuine spacefaring civilization within our solar system, all for less cost and risk than a single mission to Alpha Centauri. Maybe the real lesson is that we're asking the wrong question. It's not, can we reach Alpha Centauri? It's, should we even try? Given the costs, given the risks, given the alternatives, is Alpha Centauri the best use of our resources? Or is it vanity? Pride? A desire to say we did something impossible, even if that something doesn't actually benefit anyone? The universe is vast. Our resources are limited. Every dollar spent on an Alpha Centauri mission is a dollar not spent on solving problems here. Not spent on education, healthcare, climate change, poverty. These are real problems affecting real people right now. Alpha Centauri is a dream. A very expensive dream. Do we have the right to prioritize dreams over immediate human needs? Some would say yes. That exploration is what makes us human. That reaching for the impossible inspires us, drives us, creates technologies and knowledge that benefit everyone. The Apollo program gave us satellite communications, weather forecasting, materials science advances. Maybe an Alpha Centauri mission would do the same. But Apollo cost about $25 billion in 1960s dollars. About $280 billion in today's money. Spread over a decade. An Alpha Centauri mission would cost trillions. Plural. Over centuries. The return on investment, if any, wouldn't materialize for generations. Possibly ever. It's a harder sell. Much harder. And there's another consideration. Earth is in trouble. Climate change. Ecosystem collapse. Biodiversity loss. These aren't distant future problems. They're happening now. We're in a crisis that could determine whether human civilization survives the next century. And we're talking about spending trillions on a mission to another star system? Some would call that irresponsible. Criminal even. Fiddling while Rome burns. Dreaming of the stars while the planet dies. Maybe the message of Alpha Centauri's impossibility is that we need to focus here. Now. On this planet. This civilization. These problems. Not as a temporary measure before we reach for the stars, but as our actual purpose. Maybe we're not meant to be an interstellar species. Maybe we're meant to be a terrestrial species that learns to live sustainably on one planet. To build a civilization that lasts not by expanding outward, but by achieving balance inward. There's a philosophy in that. A wisdom. Not giving up on dreams, but recognizing which dreams serve us and which ones distract us from what matters. Alpha Centauri is a distraction. A beautiful, seductive distraction from the hard work of fixing our own world. And maybe accepting that is maturity. Growing up as a species means recognizing limits. Not railing against them. Not wasting resources trying to overcome the impossible. But accepting what is and making the most of it. Our solar system is enough. More than enough. 8 planets. Hundreds of moons. Billions of asteroids. Comets. The Kuiper Belt. The Oort Cloud. Enough raw materials and living space to support trillions of humans. Enough to keep us busy for millennia. We don't need Alpha Centauri. We want it. But want and need are different things. And wanting something doesn't make it achievable, doesn't make it wise, doesn't make it right. A child wants to fly by flapping their arms. We don't encourage that. We teach them about gravity, about reality, about working within constraints rather than against them. Maybe that's what the universe is teaching us with Alpha Centauri. Work within your constraints. Your star system is your constraint. Make peace with it. There's freedom in acceptance. Freedom in recognizing that some things are truly impossible, and that's okay. You don't have to conquer everything. You don't have to go everywhere. You can be content with what you have, with where you are. Earth is a paradise. The only paradise we know for certain exists. And we're destroying it while dreaming of other worlds. That's not aspiration. That's delusion. Fix Earth first. Master sustainability here. Learn to live within our means. Build a civilization that could last 1,000,000 years right here, in this solar system, without ever leaving. And if we achieve that, if we truly become wise stewards of our own cosmic neighborhood, then maybe, we revisit the question of Alpha Centauri. Not as escapism, not as conquest, but as mature beings who've earned the right to explore because we've first learned to sustain. But we're not there yet. We're nowhere close. We're still children, breaking our toys and demanding new ones. Still fighting over resources instead of sharing them. Still prioritizing short-term gain over long-term survival. We have no business reaching for the stars when we can't even manage one planet. Alpha Centauri sits in the sky, unreachable, and maybe that's good. Maybe we need that reminder. That boundary. That wall we cannot cross. It keeps us honest. Keeps us focused on what we can achieve rather than fantasizing about what we cannot. The impossible serves a purpose. It defines the limits of the possible. And within those limits, there's still infinite room for achievement. For growth. For wonder. We can explore our solar system. We can build habitats on Mars. We can mine asteroids. We can establish research stations on Europa and Titan. We can create rotating space stations that house millions. We can build solar arrays that power our civilization. We can become a true space-faring species without ever leaving the sun's gravitational embrace. That's not settling. That's not failure. That's working intelligently within physical constraints. And maybe centuries from now, when we've mastered our own solar system, when we've built a sustainable, thriving civilization among the planets, someone will look at Alpha Centauri and have a new idea. Some breakthrough we can't imagine today. Some loophole in physics we haven't discovered. Some technology that makes the impossible possible. And if that happens, then we go. But not before. Not until we're ready. Not until we've proven we can sustain ourselves for centuries without destroying everything we touch. The journey to Alpha Centauri begins here. On Earth. In our solar system. With learning patience. Sustainability. Cooperation. Wisdom. Those are the technologies we lack. Not antimatter engines. Not generation ships. We lack the wisdom to use what we have responsibly. And until we develop that wisdom, Alpha Centauri is better off unreachable. A goal deferred until we've matured enough to deserve it. In the end, Alpha Centauri stands as the greatest teacher the universe has given us. Not through what it offers, but through what it denies. It shows us our limits. Our smallness. Our dependence on this fragile blue world that gave us life. It reminds us that the cosmos operates on scales we cannot match, with energies we cannot harness, across distances we cannot cross. For now, the stars belong to light and time and the vast and different forces that shape them. They are not ours to claim, not ours to conquer. They are there to inspire us, yes, but also to humble us. To remind us that we are not the masters of the universe. We are its students. And we have much to learn. Alpha Centauri waits. Patient. Unchanging. 4.37 light-years away. Perhaps one day, when we have learned our lessons, when we have become something greater than we are now, we will find a way to reach it. Or perhaps we won't. Perhaps we'll realize that reaching it was never the point. The point was the looking, the wondering, the dreaming, the recognition of something greater than ourselves. The universe is vast beyond comprehension. Our lives are brief. Our reach is limited. And that's not a tragedy. It's simply the truth. We are finite beings in an infinite cosmos. And there is profound beauty in that finitude. In knowing our place. In accepting our boundaries. In making the most of what we have rather than mourning what we cannot reach. Alpha Centauri is impossible. And perhaps that's exactly as it should be. A light in the darkness. Forever distant. Forever unreachable. Forever reminding us that mystery and wonder don't require conquest. Sometimes, the greatest achievements lie not in reaching our destination, but in understanding why we cannot. And in that understanding, finding peace. The stars will wait. They've waited for billions of years. They'll wait billions more. And we, tiny and temporary, will look up at them for as long as we exist. Dreaming, wondering, accepting. And in that acceptance, finding something more valuable than any distant world could offer. We find our place, our purpose, our home, right here, where we've always been, where perhaps we've always belonged. The problem of information decay haunts any interstellar mission in ways we rarely consider. A spacecraft traveling to Alpha Centauri carries data, navigation algorithms, system schematics, repair protocols, medical databases, everything the crew might need. But digital storage isn't eternal. Cosmic rays flip bits in computer memory. 1 becomes 0. 0 becomes 1. Randomly. Constantly. Invisibly. Error-correcting codes can catch some of this. Redundant storage helps. But over decades, the cumulative damage adds up. Files become corrupted. Programs develop bugs that weren't there at launch. The spacecraft's knowledge slowly degrades, like a brain developing dementia. And unlike dementia patients, there's no caregiver. No doctor. No one to compensate for the failing memory. Imagine arriving at Alpha Centauri and discovering that critical sections of the landing procedure have been corrupted. Or the life support algorithms contain errors. Or the medical database is unreliable. You need to verify everything. Cross-check everything. But against what? The backup systems have been exposed to the same radiation. They're degrading too. How do you know what's correct anymore? Some missions might carry physical books. Printed materials that don't degrade from radiation. But books are mass. Precious mass. And books can't contain everything. You can't print the entire codebase of the ship's computer systems. Can't print every possible repair procedure. Can't print a medical textbook detailed enough to handle every emergency. The knowledge fits on silicon chips. But silicon chips are vulnerable. There's also the problem of language drift. If this is a generation ship, the people who arrive won't be the people who left. Language evolves. New words emerge. Old words change meaning. After a century, will the descendants even understand the documentation? The technical manuals were written in 21st century English. But their English has drifted. Evolved. Incorporated new slang. Lost old vocabulary. They're reading instructions written by their great-great-grandparents in a dialect that feels archaic. Foreign. And that assumes they can still read. Literacy requires maintenance. Education systems. Teachers. Books. If the generation ship's culture degrades, if education becomes less formal, if the mission's purpose becomes mythology rather than living knowledge, literacy itself might fade. The descendants might be effectively illiterate in the technical language needed to operate the spacecraft. They're living inside a machine they no longer understand. Pushing buttons out of ritual rather than comprehension. This isn't science fiction. This is anthropology. Cultures forget. Knowledge is lost. The ancient Greeks had steam engines, crude ones, but the technology was forgotten. Medieval Europe lost Roman engineering knowledge. We've rediscovered the recipe for Roman concrete only recently, 2,000 years later. If civilizations on Earth can lose knowledge, Imagine a tiny population isolated in space for generations. The knowledge hemorrhage would be catastrophic. Some propose AI systems to maintain knowledge. Artificial intelligences that don't forget, don't drift, don't lose literacy. They'd be the permanent crew, shepherding the humans, preserving technical knowledge across generations. But AI systems need maintenance too. They need updates, debugging. Someone has to understand them. And if the humans lose that understanding, the AI becomes a black box. A mysterious oracle that gives instructions nobody comprehends. Eventually, the AI fails, and nobody knows how to fix it. We're describing cargo cults in space. Descendants performing rituals their ancestors designed, not understanding why, just knowing they must. Press this button at this time. Speak these words into the communication system. Follow the green lights. They've lost the why. They only remember the what. And when something breaks, when the ritual stops working, they have no framework for fixing it. They're helpless. The spacecraft becomes a tomb while everyone's still alive. Systems slowly failing. The descendants watching helplessly as their world dies around them, unable to repair it because they've forgotten how. They know they're supposed to reach Alpha Centauri. The stories say so. The mythology promises a new world. But they have no idea how much farther it is. No idea if they're even still on course. No idea what to do when they arrive. They're ghosts haunting a machine they don't understand, waiting for salvation that may never come. And what about evolution? A century is a short time evolutionarily, but we're not talking about natural evolution. We're talking about selection pressures in an artificial environment. The spacecraft's environment is strange. Low gravity or artificial gravity. Recycled everything. Limited space. No predators. No diseases except what came with them. Different selection pressures entirely. Traits that helped on Earth might be neutral or harmful in space. Traits that were neutral on Earth might become advantageous. The population is small, so genetic drift is strong. Random changes in gene frequency. Founder effects. Over generations, this population diverges from Earth humans. Not dramatically. Not in a century. But noticeably. They're adapting to the spacecraft. To the mission environment. Becoming something slightly different. Their bones might become lighter. Why maintain dense bones in low gravity? Their immune systems might change. Why fight off diseases that don't exist? Their psychology might shift. Personality traits suited to spacecraft life become more common. Claustrophobia is selected against harshly. You can't be claustrophobic on a generation ship. Those individuals suffer more. Reproduce less. The gene patterns associated with claustrophobia, if there are any, decline. What arrives at Alpha Centauri might not be quite human anymore. Not alien. But changed. Adapted to a century of spacecraft life in ways that make them poorly suited for planetary life. Their bones are too light for strong gravity. Their immune systems are naive, having never encountered a complex biosphere. Their psychology expects small, enclosed spaces. The open sky of a planet, if they find one, might terrify them. The horizon stretching away might induce panic attacks. There's space-adapted humans trying to colonize a planet. It's backwards. They might be better off staying in orbit. Building habitats in space near Alpha Centauri rather than landing. But that wasn't the plan. The plan was to colonize a planet. To have a new Earth. Except the colonists aren't Earth humans anymore. There's something else. Something in between. And they're discovering that they don't fit in either world. Not the spacecraft they're leaving. Not the planet they're approaching. They're homeless. This identity crisis would be profound. Who are they? Where do they belong? Their ancestors left Earth to colonize Alpha Centauri. But they themselves never knew Earth. And Alpha Centauri doesn't feel like home either. They're truly interstellar. Not from anywhere. Not going anywhere. Just existing in the liminal space between stars. Between identities. Between purposes. Some might refuse to land. Refuse to continue the mission. They might decide that the spacecraft is home. It's all they've known. They'll stay in orbit, live and die in space. Let Alpha Centauri pass by unused. The mission fails not from technical problems but from existential refusal. The descendants rejecting their ancestors' dream. And Earth, receiving the news 8 years after the fact, 4 years for the signal to reach the spacecraft, 4 years for the response to come back, can do nothing. Can't intervene. Can't persuade. Can't force. Can only watch helplessly as the mission they invested everything in dissolves into philosophical paralysis light years away. This is the human element nobody accounts for. We plan missions as if humans are components. Predictable. Controllable. We design systems assuming people will follow procedures. Maintain the mission. Stay committed. But humans aren't components. We're chaotic. Emotional. We change our minds. Lose interest. Rebel against purposes imposed on us. And over generational timescales, that chaos compounds. You can't engineer humans the way you engineer spacecraft. You can't build redundancy into culture. Can't debug society. Can't patch psychology. The human systems are far more likely to fail than the technical systems. And when they fail, the mission fails. Not with explosions. Not with drama. Just with people deciding they don't want to do this anymore. Maybe that's why no one has tried. Maybe some civilizations have reached the technical capability for interstellar missions and realized that the weakest link is the crew. That sending humans is a mistake. That you need something more reliable. More committed. Less human. Robots. AI. Something that won't change its mind halfway through. But then you face the question, what's the point? If you're sending machines, not humans, what are you exploring for? Machines don't experience wonder. Don't feel awe. Don't dream of new worlds. They execute programs. Collect data. Send reports. There's no consciousness there. No subjective experience. The exploration is empty. Meaningless. A machine looking at Alpha Centauri doesn't appreciate it. Doesn't understand it. Just measures it. So we're trapped in a paradox. Humans are too unreliable for interstellar missions. But machines make interstellar missions pointless. The only way to make the journey meaningful is to send conscious beings. But conscious beings are the most likely to fail. It's an impossible optimization problem. Maximize reliability or maximize meaning. You can have both. Perhaps this is why the galaxy seems empty. Why we see no evidence of other civilizations spreading among the stars. Not because intelligent life is rare, but because interstellar colonization is impossible. Not just for us. For everyone. The physics doesn't work. The biology doesn't work. The psychology doesn't work. Every civilization reaches this conclusion eventually. Looks at the stars. Does the calculations. Realizes it's not happening. And turns inward. Focuses on their own solar system. Their own planet. Their own problems. The Fermi paradox asks, where is everyone? Maybe the answer is home. Staying home. Because leaving is impossible. Not impossible in the sense of technically challenging. Impossible in the sense of fundamentally incompatible with the nature of conscious, biological life. We're planet-bound by our very essence. Our needs. Our limitations. Our lifespans. Our psychology. We evolved for Earth. For a planet. For gravity and atmosphere and biosphere. We're adapted to this environment in a million subtle ways we don't even recognize. Take us away from it, and we start to break. Physically. Mentally. Socially. The farther we go, the more we break. Mars is hard. The outer solar system is harder. Interstellar space is impossible. And maybe we should be grateful for that. Grateful for the constraint. Because if interstellar travel were easy, we'd spread like a virus. Consuming. Exploiting. Destroying. We haven't even learned to live sustainably on one planet. Imagine us with access to millions. We'd be a plague. An ecological disaster on a galactic scale. Maybe the universe is protecting itself from us, keeping us contained until we grow up. If we ever grow up. Alpha Centauri, unreachable, is the universe's immune system, keeping the infection that is humanity localized, preventing us from spreading until we've proven we can exist without destroying everything around us. And we haven't proven that. Not even close. Every ecosystem we touch we damage. Every resource we find we exploit to exhaustion. We're not ready for other worlds. We just ruin them too. So perhaps the impossibility is a gift. A protective barrier. Not keeping us from opportunity, but protecting the cosmos from us. Until we change. Until we learn. Until we become something worthy of the stars. And if that day never comes, if we never learn, then we stay here. On Earth. In our solar system. Limited. Contained. Unable to harm anything beyond our reach. It's a humbling thought. That our greatest dreams of expansion might be the universe's nightmare. That our ambition is exactly what needs to be constrained. That the stars aren't promised lands waiting for us. They're sanctuaries. Protected from us. Safe from human touch. And they need to remain that way. Maybe the lesson of Alpha Centauri is that not everything is for us. Not every place is meant to be reached. Not every horizon should be crossed. Some boundaries exist for good reason. And recognizing those boundaries, accepting them, living within them peacefully and sustainably, that's wisdom. That's maturity. We're children pressing against a fence, frustrated we can't climb over. But the fence is there because what's on the other side isn't safe for us. Or we're not safe for it. And until we understand that, until we accept it, the fence stays up. The stars stay distant. Alpha Centauri stays impossible. Not as punishment. As protection. Protecting us from the void. Protecting the cosmos from us. A necessary separation. A healthy boundary. One we should respect rather than resent. The universe has spoken. 4.37 light-years is too far. The laws of physics make it clear. And perhaps instead of fighting those laws, instead of dreaming up impossible solutions, we should listen. Accept the message. Turn our gaze homeward. Fix what we have. Cherish what we have. Make peace with limits. Because within those limits lies everything we need. 1 star. 8 planets. Countless moons and asteroids. And one precious, irreplaceable world where life emerged against impossible odds. Where consciousness awakened. Where beings capable of understanding the universe opened their eyes and looked up at the stars. That's the miracle. Not reaching Alpha Centauri. But being here. Alive. Aware. Capable of asking the question. The journey doesn't need to be to another star. The journey is understanding this one. This system. This moment. This existence. Alpha Centauri taught us what we needed to learn. Not by being reachable, but by being impossible. The perfect teacher. The ultimate lesson. Know your limits. Respect them. And find meaning within them. That's the conclusion. That's where the story ends. Not with triumph over Alpha Centauri, but with acceptance of Earth. Not with escape to the stars, but with commitment to home. Not with conquest of the impossible, but with wisdom to know what battles to fight. We looked at Alpha Centauri. We calculated. We dreamed. We understood. And in understanding, we found something more valuable than any distant world. We found our place. The economics of interstellar travel reveals something we rarely confront. Every resource spent on Alpha Centauri has an opportunity cost measured in human lives. The money that could build a starship could also provide clean water to millions. Could fund cancer research. Could build schools. Could prevent famines. We're not just asking whether we can reach Alpha Centauri. We're asking whether we should, when people are dying from problems we could solve today. This isn't just philosophy. It's mathematics. Cold, brutal mathematics. $1 trillion on an interstellar mission versus $1 trillion on renewable energy infrastructure. One might reach another star in a century. The other might save civilization in a decade. Which is more valuable? Which is more urgent? The answer seems obvious, yet we keep dreaming of the stars while the planet burns. There's a selfishness to the Alpha Centauri dream. It's the fantasy of the wealthy and secure. People with food and shelter and safety can afford to dream of distant stars. But billions don't have those things. Billions live in poverty, hunger, conflict. For them, Alpha Centauri is irrelevant. Obscene even. A cosmic vanity project while they struggle to survive each day. And yet space exploration advocates argue the opposite. That reaching for the stars inspires humanity, drives innovation, creates technologies that help everyone. The Apollo program gave us microelectronics, solar panels, water purification systems. Maybe an Alpha Centauri mission would spark similar breakthroughs. Maybe the effort to overcome impossible challenges creates solutions to ordinary problems. But there's a difference. Apollo cost billions over a decade. Alpha Centauri would cost trillions over centuries. The return on investment timescale is completely different. Apollo paid dividends within a generation. Alpha Centauri wouldn't pay anything for multiple generations. How do you justify that? How do you convince someone struggling today that we should invest in something their great-great-grandchildren might benefit from? If they benefit at all. The political reality makes it impossible. Democratic governments operate on election cycles. 2 years. 4 years. 6 years. Leaders need to show results within their term. An interstellar mission shows no results for decades. No politician can champion it. No voter can be mobilized by it. It's too abstract. Too distant. Too uncertain. Authoritarian governments might have longer time horizons. Single-party states. Dictatorships. They're not accountable to voters. They can pursue multi-generational projects. But they're also unstable. Regimes change. Priorities shift. A dictator launches an interstellar mission, and their successor cancels it. Redirects the resources to military spending, or palace construction, or suppressing dissent. The mission dies not from technical failure but from political whim. Even if a government stayed committed, even if somehow political will sustain for a century, there's the problem of public support. People would see the spending, see the resources flowing into a project that benefits nobody alive. That resentment builds. Eventually, it becomes politically untenable. The mission gets cancelled, or sabotaged, or simply starved of funding until it collapses. We can't even maintain infrastructure that benefits us today. Bridges crumble. Roads decay. Water systems leak. All because we won't spend money on maintenance. It's not exciting. Not visible. Not politically rewarding. If we can't maintain bridges, how would we maintain commitment to a century-long mission to another star? The idea is laughable. And there's another problem. Technological obsolescence. Let's say we start building a generation ship today. 20 years into construction, someone invents a new propulsion system. Twice as fast. Half the cost. Do we scrap the current ship and start over? Or do we continue with inferior technology because we've already invested so much? It's the sunk cost fallacy on a cosmic scale. But if we do start over, we waste decades and billions. And 20 years after that, another breakthrough happens. Do we start over again? At what point do we actually commit? How do we know we've reached the optimal technology? We don't. We can't. Technology keeps advancing. The best strategy might be to wait forever, always expecting a better solution tomorrow. This is called the wait calculation. At what point is the technology good enough that you should launch, knowing it will be obsolete before it arrives? If you wait too long, you never go. But if you go too early, you waste resources on an inferior mission that might be overtaken by a later mission using better technology. There's no right answer. Just increasingly painful trade-offs. Imagine launching a generation ship in 2100, traveling at 5% of light speed, arrival time around 2185. But in 2120, fusion drives are perfected. A new ship launches, traveling at 15% of light speed. It overtakes the generation ship and arrives in 2150. The first crew, still decades from arrival, learns they've been beaten. Their mission is now redundant. They've sacrificed everything for nothing. Their entire lives wasted on a pointless journey. What do? Continue? Turn back? They can't turn back. Not enough fuel. Can't speed up. Can't change course. They just continue, knowing they're obsolete. Knowing another crew already reached their destination. Knowing history will remember them as the slow ones. The redundant ones. The waste. That psychological devastation would be total. Your entire purpose gone. You're still decades from arrival, and it doesn't matter anymore. Some would probably kill themselves. Others would fall into catatonic depression. The mission would collapse not from technical failure but from existential despair. They'd arrive, if they arrive, as broken shells of people, traumatized by their own irrelevance. And this assumes peaceful overtaking. What if it's not peaceful? What if the second mission views the first as competitors? As claim jumpers? Space law is murky at best. Who owns Alpha Centauri? First to arrive? First to launch? First to claim? If multiple missions from multiple nations or corporations are heading to the same system, conflict becomes inevitable. The second mission might actively sabotage the first. Send missiles ahead. Destroy the generation ship. Eliminate the competition. It's darker than piracy. It's premeditated murder of thousands, committed from millions of miles away, to secure territorial claims to a planet nobody's even seen up close. And by the time anyone on Earth knows about it, 8 years have passed. Too late to intervene. Too late to punish. The crime is committed in the darkness between stars where law cannot reach. Or consider corporate missions. Private space companies racing to Alpha Centauri. Whoever arrives first claims the resources. The intellectual property. The glory. The profit. Competition becomes cutthroat. Sabotage. Espionage. One company's mission mysteriously fails. Was it technical malfunction? Or did a rival arrange it? We'll never know. Can't investigate. Can't prosecute. Corporate murder on an interstellar scale, completely unprovable. The Wild West in space. Except there's no sheriff. No federal marshals. No law except what you can enforce yourself. And enforcement across light years is impossible. You're on your own. If someone wrongs you, there's no recourse. No justice. Just a void in your own resources. It's not exploration. It's lawless frontier brutality where might makes right and morality dissolves into vacuum. This is what happens when we project human nature onto interstellar scales. The ugliness doesn't stay on Earth. It follows us. Our conflicts. Our greed. Our violence. We carry them like viruses into every environment we enter. And in space, with no constraints, no authorities, no consequences, those viruses metastasize into something monstrous. Maybe that's another reason the galaxy seems empty. Not because interstellar travel is impossible, but because civilizations that achieve it destroy themselves in the process. The technology capable of crossing interstellar distances is also capable of extraordinary destruction. And species foolish enough to attempt interstellar colonization are probably foolish enough to use that destruction against themselves. Nuclear propulsion could work for interstellar travel. Orion drives. Detonating nuclear bombs behind a spacecraft to propel it forward. Crude but effective. Except now you're building thousands of nuclear weapons and putting them on a spacecraft. What stops someone from retargeting that arsenal? From turning the ship into a weapon? One rogue crew, one zealot, one madman, and suddenly you have a relativistic missile heading toward Earth or toward the other mission or toward whoever the attacker wants dead. At relativistic speeds, even a small object is catastrophic. Kinetic energy scales with the square of velocity. At 10% of light speed, a 1 kilogram projectile hits with energy equivalent to the Hiroshima bomb. Now imagine a spacecraft massing thousands of tons moving at that speed. If it hits a planet, it's an extinction event. larger than the asteroid that killed the dinosaurs. Deliberate. Unstoppable. Announced by nothing except maybe a transmission seconds before impact, traveling at the speed of light, giving no time to react. Interstellar travel doesn't just enable exploration. It enables planet killing. And once multiple missions are en route, once humanity is scattered across interstellar space in vessels we can't communicate with in real time, we lose control. We've created planet killers we can't recall, can't stop, crewed by people who've been in transit so long they might not even remember why they launched. Who they are. What they're supposed to do. The existential risks compound. It's not just about reaching Alpha Centauri anymore. It's about surviving what we create in the attempt. The technologies. The weapons. The isolated populations with access to devastating power and no oversight. We might destroy ourselves before we ever arrive. Or arrive only to destroy whatever we find. Or each other. Every solution creates new threats. Antimatter propulsion? Now you're handling kilograms of the most volatile substance imaginable. A containment failure releases energy measured in megatons. Your antimatter-powered ship becomes an antimatter bomb. Everyone aboard dies instantly. Everyone near them dies. The ship disintegrates into expanding plasma. Mission over. Laser propulsion? You're building gigawatt laser arrays that can be retargeted toward Earth. Toward cities. Toward rival nations. The weapon potential is obvious. The geopolitical implications terrifying. Who controls the lasers? What stops them from using that power for coercion? For war? The infrastructure for interstellar travel becomes the infrastructure for superweapons. Inseparable. Indistinguishable. And the silence continues. We build these systems. We prepare these missions. We create these dangers. And we hear nothing back. No signal from Alpha Centauri. No transmission from anyone out there. The electromagnetic spectrum remains eerily quiet except for natural sources. Pulsars. Quasars. Cosmic microwave background. But no voices. No civilizations. No one saying hello? That silence grows heavier with each passing year. We've been listening since the 1960s. SETI. The search for extraterrestrial intelligence. Decades of searching. Nothing. Either we're alone, which is terrifying. Or we're not alone, but no one's talking, which might be even more terrifying. Why aren't they talking? What do they know that we don't? Maybe they know that announcing your presence is suicide. That interstellar-capable civilizations are dangerous. That the first rule of galactic survival is silence. Stay hidden. Stay quiet. Don't let anyone know you're here. Because the civilization that finds you might not be friendly. Might view you as competition. As threat. As resource to be exploited. Dark forest theory. The galaxy is a dark forest. Every civilization is a hunter. Moving silently through the trees. The first to reveal their position dies. Shot by someone they never saw. Someone who struck preemptively because in the dark forest, trust is death. Better to kill than be killed. Better to hide than risk exposure. If that's true, if the galaxy operates on dark forest rules, then SETI isn't just futile. It's dangerous. We're broadcasting our location. Announcing ourselves. Shouting into the forest, here we are. Come find us. And if anyone does, if anyone picks up our signals and decides to respond, they won't respond with greetings. They'll respond with weapons. Light-speed kill vehicles. Relativistic projectiles launched from across the galaxy, taking centuries or millennia to arrive, hitting without warning at speeds that make defense impossible. We'd detect the impact seconds before it hits. Not enough time to react. Not enough time to pray. Just sudden extinction. That's one solution to the Fermi paradox. The galaxy is full of civilizations. But they're all hiding. Terrified of each other. And we, naive children, are shouting into the darkness, inviting something to find us. Kill us. Silence us before we become a threat. Or maybe the answer is simpler. Maybe interstellar travel is impossible. Not just difficult. Not just expensive. Truly, fundamentally impossible for biological life. And once civilizations realize this, once they exhaust every avenue and accept the truth, they stop broadcasting. They turn inward. They focus on virtual realities, simulated universes. They abandon physical exploration for digital infinities. Why struggle against the impossible when you can create perfect worlds inside computers? Why cross light years when you can simulate galaxies? Why risk the void when you can live forever in digital paradise? Maybe every civilization reaches this conclusion. Physical space is too hard, too dangerous, too empty. Digital space is easier, safer, more rewarding. And so they vanish from the observable universe. Not dying, not expanding, just withdrawing, becoming invisible. Digital ghosts and machines, experiencing infinities we can't imagine, unbounded by physical law. They're out there, maybe everywhere, but we can't see them because they're not in our reality anymore. They've transcended it, left it behind. If that's our future, if that's where we're heading, then Alpha Centauri truly doesn't matter. It's irrelevant. A physical destination in a universe we're leaving. We'll build our infinities here, in server farms and quantum computers. We'll explore digital space, not physical space. We'll become post-physical, post-biological, post-human. And in that transition, Alpha Centauri fades from relevance. Just another star in a sky we no longer watch. Because we're not looking outward anymore. We're looking inward. Into realities we create. Control. Perfect. Why venture into the cosmos when you can build better ones yourself? That's the endpoint. Not starships. Not colonies. Not galactic empires. Just civilizations dissolving into digital immortality, abandoning the physical universe as too crude, too limited, too bound by laws they can't change. The final surrender. Not to impossibility, but to something better than possibility. Something beyond physics entirely. Alpha Centauri watches this, waiting for visitors that will never come. Not because they can't travel, but because they chose not to. Because they found something else. Something that doesn't require light years of travel or centuries of waiting or impossible technologies. They found infinity within. And outer space, once the ultimate frontier, became just another place they used to care about. Long ago. Before they evolved past caring.